Good afternoon, my name is Danil Solomonov. The topic of my report is fatigue damage accumulation in laminated carbon epoxy plastics. The relevance of the problem is determined by the following factors. The first one is expanding the use of composites is an important condition for competitive ability in many areas. The next one is dynamic loading or vibrations is an inescapable factor of composite operating conditions. Also, fatigue failure is the most common cause of failure of machine parts. The next one is ensuring resistance to high cycle fatigue is the most important condition for the use of composites. And the need of experimental data and mathematical models for understanding the process of fatigue damage accumulation and predicting the durability and reliability of composites. The last factor is the variety of polymer composite materials and the variety of damage accumulation mechanisms. Examples from the aviation are shown on the slide. The purpose of present research is to obtain experimental data on the change of the elastic characteristics of layered composites as fatigue damage accumulates. It should be emphasized that the task is to study 4 elastic parameters of the laminate monolayer: 2 Young's models, shear modulus, and Poisson ratio. The objectives of that investigation are shown on this slide. The object of research is laminated carbon fiber reinforced plastic consisting of differently oriented identical layers with unidirectional reinforcement. 2 types of samples made from were studied. Information about them shown on the slide. On this slide we can see the research scheme. Fatigue tests were carried out on accordance with ISTM D standard using the Testronic 50 resonance testing machine, a tensile mode cyclic loading with the constant stress amplitude and asymmetry ratio of 0.1 was realized. The loading frequency was 40 Hz. The temperature of the sample was monitored using an infrared camera. Although the loading was carried out with the relatively high frequency, the temperature did not exceed 20 degrees. The load amplitude was chosen so that the lifetime N of the sample was about 1 million cycles. For this purpose, the fatigue curves obtained in advance were used. The relative stress amplitude was 0.64 for the first type of samples and 0.3 for the second type. The method of scanning laser vibrometry was used. The sample was attached to a rigid frame on thin elastic. Sample's vibrations were excited by an acoustic shaker and recorded using a scanning laser vibrometer PSV 403D. Thus, the tests were performed without contact of equipment with the sample. This made it possible to determine with high accuracy the first 8 natural frequencies in the range up to 2000 Hz. The results of model analysis before the fatigue test for the first group are shown on the slide. The results of model analysis before the fatigue tests for the second group are also shown on the slide. On this slide, we can see the scheme for identifying the elasticity characteristics of a monolayer based on the results of model tests of samples. A finite element model analysis were used to identify the elasticity characteristics. The main idea and Phi model are shown on the slide. Now let's move on to the results. The slide shows the changes in the natural frequencies during fatigue damage. That slide shows the changes of the elastic characteristics of a monolayer with the fatigue damage. On this slide, we can see a comparison of elastic characteristic changes in different groups of samples. This slide shows us the results of non-destructive tests on different stages of fatigue damage for the first group of samples. The next slide shows us the results of non-destructive tests on different stages of fatigue damage for the second group of samples. On this slide we can see typical examples of destruction for both groups of samples. The results obtained during the research are presented on the slide. Thank you for attention.